This video will introduce the solubility rules and ultimately the precipitation reactions. A precipitation reaction involves a product that is insoluble in aqueous solution, and when we write these reactions, we can write them in one of several ways. The first way of writing the reaction is referred to as the molecular equation. This is when we write the formulas of all the compounds such that we have all of the ions present. So, for an example, is we have an aqueous solution of lead nitrate, as shown in beaker 1. That can be combined with a solution that is in beaker 2 that has potassium iodide. In this particular case, when those two solutions are combined, the ions can exchange with one another so that the anion of the potassium iodide ends up with the lead of the lead nitrate, which forms an insoluble compound and is then turned into a solid, as you see on the right. The other product is a soluble ionic compound, potassium nitrate. You also see that the balanced chemical reaction involves having the stoichiometric coefficients of 2 in front of the potassium iodide and the potassium nitrate. In addition to the molecular reaction, we can write what's referred to as the complete ionic equations. In this case, any compound that is an electrolyte, a strong electrolyte, are written such that we have the ions that would be actually present in aqueous solution. So, for example, since lead nitrate is an ionic compound that is very soluble in water, we would then now write this formula as the lead 2 plus ion, Aq, and since there were 2 nitrates in the formula, we also then have to write in the complete ionic reaction the 2 nitrates with the stoichiometric coefficient in front of the nitrate. In the second beaker then was potassium iodide. We would then have 2 potassium ions that are now present in the solution, and in addition to that we have 2 iodide ions. If we then combine those 2 beakers, again we produce the insoluble lead iodide, which is the solid that is formed, but the remaining potassium nitrate is an electrolyte and is a strong electrolyte, so that we write the formulas so that we have 2 potassium ions and 2 nitrate ions. The final way one can go about writing a chemical reaction involving electrolytes is to write the net ionic equation. In this case, we have to remove the so-called spectator ions, which are the ions not directly involved in the chemical reaction. So, as an example here, if this is our complete ionic reaction from what we did before, we notice that there are ions that are identical on both sides of the arrow. In this case, we see that the nitrate, which is on the reactant side, is also the same as the nitrate that is on the product side. So in fact, that formula is completely unchanged. Likewise, the potassium ions are both on the reactants and product side, so that also is a spectator ion, and they can be removed from the reaction, and so that leaves us with the ions and the precipitate that will be present in the the net ionic equation. So, ultimately, by removing those and writing the reaction again, we come up with the overall net ionic reaction. This slide gives us a sense of what we would actually observe if we went into the laboratory and did this solution. So on the left-hand side, we have our two beakers that contain the lead nitrate and the potassium iodide solutions. In the case of the combining of those two solutions, we get the immediate formation of the yellow powder that is then the so-called precipitate. This is the lead iodide. And after mixing those two solutions and allowing the solid to settle, you would end up with the solid on the bottom of the beaker, as you see on the right, and the potassium iodide solution, which is then the clear liquid that appears on top of that yellow solid. Any kind of reaction that is going to produce an insoluble species in aqueous solution is referred to as a precipitation reaction, and so we can use our solubility rules to predict which of the possible combinations of ions will produce an insoluble species and therefore result in a precipitation reaction. The actual solid that is formed is referred to as the precipitate. On this slide, we will go through the solubility rules. These are a set of guidelines that you should memorize and will help us predict whether or not a precipitate will form when we combine aqueous solutions. The first rule is that we have soluble species if the ionic compound contains a group 1 ion. And the other ion that also produces compounds that are soluble is if you have the ammonium ion. So if you have an ionic compound with lithium, sodium, potassium, cesium, or ammonium ion as the first ion in the formula, this will generally be a soluble compound. There are no exceptions to this rule. The second rule is if the negative ion, the anion, is acetate, perchlorate, or nitrate, those are always soluble, and so there are actually no exceptions to this rule either. The third is that we have things like chlorides, bromides, and iodides, the so-called halides. If the anion in your formula happens to be one of these ions, probably that compound will be soluble. However, there are some important exceptions to this. If the cation is silver ion or mercury 1 ion or possibly mercury 2 ion and lead 2 plus ion, then we actually have an insoluble halide complex and they would potentially form precipitates. The final is that most sulfates are soluble. Again, there are some important exceptions that you'll need to memorize. If the positive ion associated with the sulfate is a group 2 ion, such as calcium 2 plus, strontium 2 plus, or barium 2 plus, those will be insoluble. Likewise, if we have silver or mercury 1, mercury 2, or lead 2 plus, those are also insoluble sulfates. On this side, we will discuss the solubility rules for the ions that generally form insoluble compounds. And so, first example here is carbonate. Most carbonates are insoluble in aqueous solution. The important exceptions are if the positive ion associated with the carbonate is a group 1 ion, which we had discussed on the previous slide. There are no exceptions for the group 1 ions. And likewise, if we have ammonium ion with carbonate, that would produce a soluble compound. Likewise, phosphates are generally insoluble with the same exceptions as the carbonates. So if you have a group 1 ion or ammonium, alright. And then we have sulfides. The sulfides are generally insoluble, with the exceptions being the group 1 ions, ammonium, calcium, strontium, and barium. Then finally we have the oxides and the hydroxides. The oxides and hydroxides are generally insoluble, except if we have group 1 ions or calcium, strontium, or barium. Once you have committed the solubility rules to memory, you should be able to predict whether or not various compounds are soluble or not. And so, for example, in our first case here, we have barium carbonate. Hopefully you remember that most carbonates are insoluble. Barium is not an exception to that rule, and therefore we would expect barium carbonate to be insoluble. The second compound here is potassium carbonate. Again, most carbonates are insoluble, but potassium is one of the exceptions. Whenever you have a group 1 ion, we will generally have soluble compounds. So this indeed is a soluble compound. The third example here is lead sulfate. Most sulfates are soluble, but lead 2+ happens to be an exception to that solubility rule. So in fact, this is insoluble. The fourth example is ammonium phosphate. Most phosphates are insoluble, but the ammonium ion is the exception, and so as a result, this is a soluble compound. And then finally we have iron 3 perchlorate. Right? Most perchlorates are soluble, and iron is not an exception to that rule, so this is a soluble compound.